In this video, I will cover the rest of my tutorial questions. I know a lot of people are waiting for this. I got a bunch of emails asking for this already. Here it comes. So we'll do question 2 first. This is our first question we haven't done yet. This was a quiz question from, I don't know what was a quiz question, but anyway, they want you to show that the sum from I equals to 1 to 4i squared equals to the sum from 1 to 4i plus 2 to 4i plus 3 to 4i plus 4 to 4i. Well, what can you do? In this case, you don't need induction, obviously, for obvious reason why it's to the power 2 to 4, right? It's not to n, it's not to it's not for all natural number or something, so you don't need induction. What you can do is you can just use algebra. So what I really say is starting from something simple, like something here, to this is kind of hard, because how are you going to expand it? You do not know. So what I really do is I start from the complicated part, because, well, you can open it and try to simplify it and see if you can get this eventually. So that's what I'm gonna do. I'm gonna start with my right hand side. So proof, let's start from the right hand side. So sum from I equals to 1 to 4, I plus sum from I equals to 2 to 4i plus sum I equals to 3 to 4i plus sum I equals to 4 to 4i, and this equals to what? The first term is 1 plus 2 plus 3 plus 4. And the second term is 2 plus 3 plus 4. I'm going to use different colors so it's clear. So this one is orange here. Okay. And let's make it green. Green is green here. And the third term, let's say blue is gonna be blue, so this is gonna be 3 plus 4, right? And then lastly, white is gonna be white, so from 4 to 4, so that's just gonna be 4. Now what do? You can collect the like terms. Or, in other words, you can count the number of 1s, 2s, 3s, and 4s. So this is what I did. I count number of 1s, 2s, 3s, and 4s. That's what I'm doing. So how many 1 do I have? I have 1, so it's 1 times 1. Plus, I have 2 2s. And I have 3 3s. And I have 4 4s. Okay? And this is exactly the right hand side. And that's it. That's this question. I wouldn't call it straightforward, but I think it's easier than a lot of your quiz questions. I don't think your quiz question will be this simple. Most likely you'll have induction, which is what we're gonna do for now. So now I want to use induction to prove something that's a summation identity. And I noticed that there is a typo. I don't know if anyone of you noticed that. Where is my typo? That should not be 1. Because if this is 1, I would just call it 3. So I'm guessing this is I. I'm not sure, to be honest. I'm just guessing. It's pretty normal to make it a 1 instead of I. So We'll see. When we reach there, we'll see if my guess is correct. So let's change it to I for now, and let's try to use induction. So proof. We're gonna use induction on I. So let's proceed induction. Proceed by induction on N, not on I. Sorry. Induction on N. Okay, and the first thing is my base case. Since they are asking to prove for all N in natural number, okay, and well, natural number starts with 1, so my base case is 1. So base case is 1, your N equals to 1, so 1 N equals to 1. What's on my left hand side? My left hand side would have well, if this is 1, so it's from 1 to 1, so you only have one term, 1 is equals to 1, so that's gonna be 1 plus 1 times 1 plus 2, and top is 1, so that's gonna be 1 over 2 times 3, that's 1 over 6. Right hand side would be 1 over 2 times 1 plus 4, which is also 1 over 6. Sorry, I have a cold, so it's quite hard for me to talk. Okay, and here we can see, well, left hand side equals to right hand side, so my base case holds. Or I'm too lazy to write, so I'm just gonna use a check mark. This is good. Do you wanna come in? Okay, my cat just came in. Now we do inductive hypothesis. So inductive hypothesis. Why did I write this? This is so long. Let's assume, what do I assume? I assume this and change N to K. So let's assume from I equals to 1 to K, 1 over I plus 1 times I plus 2. Again, I'm actually not sure if this is correct because I had typo. So we'll see. Okay, for some K in natural number. And now, this is your inductive hypothesis. Now let's do induction step. What is your induction step? Induction step. So remember, you want to show for K plus 1. So what do you want to show? You want to show here change to K plus 1, here change to K plus 1, here is K plus 1. Okay, so you want to show this holds. In order to do that, well, you cannot let them equal first because that's what you need to prove, right? So you cannot start with what you need to prove. So in this case, what you can do is, what do you want? What do you want? In this case, you can either start with the left hand side or start with the right hand side. Okay? I always start with this side because, again, how are you gonna go from here to here? Like, I don't know how. To be honest, I have no idea how. But from here to here is possible. Why? Let's write it down first. So we need to consider this. I equals to 1 to K plus 1. And it's 1 over I plus 1 times I plus 2. Okay, look like this. What do we do now? Okay, one thing I always say is remember, you want to use your inductive hypothesis. Okay, again, you want to use your inductive hypothesis. I'm going to write it down. You want to use your inductive hypothesis. That means you want this to show up somewhere. I want this to show up somewhere, so I'm gonna if I want this to show up, how can I do that? It's summation, so it's this is this term adding from I to 1 to k plus 1. I can also do that it's adding from 1 to k and then add an extra term, which is the last term. So this equals to I equals to 1 to k 1 over I plus 1 times I plus 2. So this is adding from 1 to k, but I need to add the last term as well. So let's add last term. So the last term is when I equals to k plus 1, so that's going to be k plus 1 times k plus 1 plus 2, and top is 1. Okay? This step is where a lot of people will be confused about because, well, if you're confused, you do not understand summation completely. That's all I can say. Okay, summation means you add from I equals to 1 till whatever number is here. So this is from I equals to 1 to k plus 1. Okay, you can also add from 1 to k first, and then add the last term, which is when I equals to k plus 1. So they are equal. Now, sorry, you have your inductive hypothesis here. Okay, remember this is what you want to use, and you have it already. Then what do you use? What do? You use it. Okay, so you want to use it. You want to use your inductive hypothesis. You know this equals to what? Equals to this. Right, so you change this to here. So let's write it down. So this equals to k over 2k plus 4. Okay, and the rest you just add them back together. I'm going to simplify it a bit. So that's going to be k plus 2 times k plus 3. Okay, now you have this. Remember, you want to get to this, changing this to plus 1. So, well, you only want one term. Now you have two terms. So what I'm going to do, I'm going to common denominator. So, common denominator, this is what? This is also 2 times k plus 2, right? So, common denominator, that's going to be 2 times. Oopsie. That's going to be 2 times k plus 2 times k plus 3, and top you have k times k plus 3 plus 2. So this is what I have. Now I'm gonna open the brackets at the top. That's k squared plus 3k plus 2, and bottom you have the same thing. However, well, top, what's top? Top, you can also write it as what? Pretty clearly, it's 3, so we need 1, 2, plus 1 plus 2. So k plus 1 times k plus 2. Right, and bottom you have 2 times k plus 2 times k plus 3. And hello, they canceled out, right? So since they canceled out, you get k plus 1 over 2k plus 6. Are you down? No. Why are you not down? Still doesn't look like this with k plus 1. So what do I want? I want k plus 1 over 2 times k plus 1 plus 4. 2 times k plus 1 plus 4. That's exactly k plus 6, okay? So my last step is I just need to write it in that form. So k plus 1 over 2 times k plus 1 plus 4. That's what you want, so as required. And now you can make your conclusion. My conclusion, so conclusion. That's it. Okay? So, going back, induction again. you have base case. Your base case depends on what you need to prove, okay? For example, they ask you to prove for all natural numbers, then you start with 1 because, well, the first natural number is 1. If they ask you to prove for all natural number greater than or equal to 3, then you start with 3, okay? Your base case depends on what you need to prove. Your inductive hypothesis is whatever you need to prove, but change all the n to k. Or you don't even need to change it. You can use k if you really want to, and if you use k here and here, then you need to prove for k for n. If you use n here and n here, then you need to prove for n plus 1. It's the same thing. You can do that as well. Okay, just my habit is I always use k. Anyway, so you want to assume whatever you have here is true for some k in natural number. Again, for some k in what? In natural. Okay, those are common mistakes. For some k in natural, it's not for any, not for all. And then you have induction step. Remember, for your induction step, you want to use your inductive hypothesis, right? Because you want to use it, you want it to show up somewhere. Okay, so you observe this and your inductive hypothesis, you look at them, compare them, you're like, oh, what's missing? How do I make my inductive hypothesis appear? Because I want to use it, okay? So because of that, I know, oh, I need this term. And if I add another term, which is the last term of this, then they are equal. Once you have your inductive hypothesis somewhere, you can use it. And when you use it, you need to tell me by IH. Okay, you should always refer it by IH. And the rest is just computation. Sometimes it's easier if you write down what you need to prove. In this case, well, it's pretty obvious, but sometimes it gets really complicated. So if it gets complicated, sometimes it's easier if you plug in k plus 1 over something and then simplify that a bit and see what you need to get. I'm not asking you to do both directions. That's just your rough work, by the way. Okay, that's it. That's all I wanna say for this question. Before I move to the last one, which a lot of people wanna do, I wanna talk about marking scheme. Of course, we wanna talk about marking scheme. Okay, so for example, if this question worth 4 marks, so use another color. So green is for 4 marks marking scheme. Okay, if this is 4 marks, then this is half. This is half. Okay, and you realizing this will be half as well. So half. This is half. So that's 2 marks. Oh, you don't even need. Then this is probably gonna be 3 marks because there isn't that much to do. So we change it to 3 marks. So half, 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 and the rest is half. And reaching the last part is half. So getting from here to here is half and half. Okay, not too, the half is not too specific step. It's just after this, the whole thing is 1. So if this is, hold on, that's not 3. 1, 2. Oh, it is 3. Never mind. Okay, I couldn't count before. So if it were 3 marks, this is how we're gonna mark it. And a lot of you are are asking if you need to state your predicate. If you ever used it, then you have to. If you never used it, then you don't have to. And you might ask, if I use the predicate and how the marking scheme is gonna change. I don't think it's gonna change anything if you define your predicate. So for example, if you have Pn, you use Pn here and you said assume Pk is true for some k natural number, then how this marking scheme is gonna change? Nothing's gonna change. It still look the same, but if your Pk, I don't think you'll lose mark here because it's pretty simple. But if you write Pk and you did not define your Pn, you won't get this 0.5. Okay, you'll lose 0.5 for not defining or getting the wrong Pn. That's how it works. Yeah, basically. And for this question as well, so base case is going to be half, inductive hypothesis is going to be half mark, and let me see where else worth half. So this step is probably half marks because it's pretty a key step, so that's 1.5, and I would say distribution part will be half mark, and after distribution half mark, getting the last part half mark, so something like that. It really depends on the question. Okay, that's what I'm gonna say. So this, if this works, 3 marks. If it's 4 marks, then we might have more marks for inductive hypothesis or base case. Depends on which one is harder. But anyway, last question. This is one a lot of you asked me to do, so we'll do it now. I'm kind of tired. Let's do it. So, for what natural number n the following inequality holds true? Let's try this. So, they asked you for what natural number, so some of them might not satisfy, so you need to check. N equals to 1, n equals to 2, and so on. So, since we know it's natural number, I'm gonna start with n equals to 1. So, when n equals to 1, 3 to the power of, I'm going to use left hand side, right hand side. So left hand side is 3 to the power of 1, which is 3. Right hand side is 1 to the power of 3, which is 1. And obviously this is less greater than right hand side. So this is good. When n equals 2, left hand side is 3 to the power of 2, which is 9. Right hand side is 2 to the power of 3, that is 8. And left hand side is greater than right hand side. So this is good as well. Okay, let's check for 3. Left hand side is 3 to the power of 3, that's 27. Right hand side is also 3 to the 3, so that's 27 as well. Well, this case fail because it's not strictly greater than right hand side, so we don't want this. What about 4? Left hand side is 4 to the power of 3. No, it's 3 to the power of 4. Oh my god. 3 to the power of 4, so 3 times 27. 81. And right hand side is 4 to the power of 3, so 16 times 4 is 64. And clearly left hand side is greater than right hand side, so good. You can check 5. I think 5 is obvious. Now this function is gonna move much faster than this function, because it's like this. One is like this, right? The other one is like this. This. Anyway, it's gonna go much faster. It's exponential. It grows really fast. That's calculus. Back to 102. So I think starting from now, we will have 3 to the power of 1 is greater than n to the power of 3. So I'm gonna make a claim. My claim is for any natural n that's greater than or equal to 4, my 3 to the n is gonna be greater than n to the power of 3. Okay, so this is my claim. Now I need to prove it. So let's proceed by induction. You don't really need to write the sentences. Well, there's no other variables. You only have n. It's not like you have multiple variables. So let's just do base case. Base case holds. Well, why? We checked it already. See above. Okay, see when n equals to 4, that's your base case. Inductive hypothesis. So I'm gonna assume 3 to the power of k is greater than k to the power of 3 for some natural k that's greater than or equal to 4. Okay. And now I consider okay, now consider, I'm so sleepy now. Now consider 3 to the power of k plus 1. Okay? Oh, okay. Who texts me? Let me check my message for a moment. Oh, got a DM. I don't check DM, by the way. If you DM me, I barely check DM. Usually I see it, I click it, and I just go back to the server. Consider 3 to the k plus 1. I want to show it's greater than, so I want to show this is greater than k plus 1, k plus 1 to the power of 3. In order to show that, remember, you want to use what? You want to use your IH, okay? You want to use your IH, so we want to write this, we want to write it and have your IH appear somewhere. What's your IH? This. You want 3 to the power of k appear somewhere. That's what? That's 3 to the k times 3. So I have my IH here. This is my IH. Let me change it to another color. This is my IH. This is my IH. So what I'm going to do, I'm going to use it. I know my IH is greater than k cubed. What does that mean? That means my whole thing is greater than 3 times k cubed. This is a place people will ask me why. I know. Although none of you are here, I know you will ask me why. Why? Because we multiply by 3 on both sides. That's why, okay? Then you can get this. Do you see? That's why. I kind of know your question already, even if you are not here. And so I showed that this is greater than this. So what do I need to show now? I need to show this is greater than or equal to k plus 1 to the power of 3. So that's my rough work. It's an inequality, you know, inequality we like to use rough work. So rough work. Rough work. What do we want to do? I want to show 3 to the k cubed is greater than or equal to k plus 1 to the power of 3. Okay? they both have power of 3, so I'm gonna move this power of 3 to the other side. Then I can combine them together. So it looks like this, which is the same as 1 plus 1 over k cubed. Okay, and your right hand side have power of 3, so I'm gonna do this to remove the power of 3. Okay, I know my k is greater than or equal to 4, so that's what I want to reach to that part. So I'm gonna move 1 to the other side. What does this mean? When we get here, what does this mean? This means that k is greater than or equal to 1 over 3 root 3, no, cube root 3 minus 1. Now you need to think, is this right? Is it? What's cube root of 3? I don't know. I actually don't know. 1 cube is 1, 2 cube is much larger than 3, so it's between 1 and 2. Let's try 1.5. So 1.5 is 3 over 2. Cube is 27 over 8. 27 over 8 is around 3.4-ish. So it's slightly less than 1.5. So I know this is slightly less than 1.5. So minus 1 is going to be slightly less than 0.5. 1 over 0.5 is 2. But it's slightly less, so you are dividing the smaller number, you'll get a big number. So it's slightly greater than 2, but, well, k is greater than 4, so it's definitely greater than 2, so this is good. Okay, hopefully you got what I said. My whole point is my k is actually greater than or equal to this, because it's greater than 4, and this number is less than 4. So we're good. Now, go back to your proof. We know that. So you can start with k greater than or equal to 4. So we know since my k is greater than or equal to 4, then 1 over k is less than or equal to 1 over 4. Right? And this is going to give me, so plus 1 on both sides is going to be less than or equal to 1 plus 1 over 4. Right, so that's 1.25. That's going to be less than or equal to this. Why? Because, well, this is slightly less than 1.5. This is 1.25, so it's that's good. So now what we have is I have this is less than or equal to this. Now take power 3 on both sides. So 1 plus k, 1 over k to the power of 3 less than or equal to 3. So let's write it. So you're doing it backwards, so I want to write it in this way. So this is k plus 1 cube over k cube is less than or equal to 3. So k plus 1 cube is less than or equal to 3k squared. We know this is less than 3k plus 1. So I proved that 3 to the power of k plus 1 is greater than k plus 1 to the power of 3. Okay, so by PMI, we know that by principle of mathematical induction, 3 to the n is greater than n to the 3 for all natural. n greater than or equal to 4, but that's not our conclusion. Combine with above. We know that 3 to the power of n is greater than n to the power of 3 for all natural minus 3. Okay, so it works for all the natural number but 3. 3 doesn't work. 1 and 2, they are good. 4, good. 5, good, and so on. They're all good. So, every natural number but 3. That's it. I'm so glad we're done with this. Okay, stop emailing me. Stop DMing me. I finished my to-do list for today. It's before the end of Friday, so I made my promise. Did I make any other promise? I think I did not. So we're done here. I will see you guys next week.